With that, I want to introduce Dr. Ozan Ozdemir from Northeastern University. He'll be talking to us about advanced empirical and computational methods. So with that, Ozan?
Hi, can you hear me?
Yeah.
Okay. I'll be putting up my slides right now. Can you see that okay?
Yep. Yeah.
Sounds good. Right, I'll get started. Okay. Hello, everyone. I'm Ozan Ozdemir. I'm a senior research scientist at Northeastern University's cold spray additive manufacturing laboratory. And today's talk is going to be on advanced computational and experimental methods in cold spray, especially focusing on methods that we use for predicting particle impact velocity and temperature profiles. Throughout the presentation, I will be showing my work as well as the work of my colleagues who are listed on the slide. At Northeastern University, we have a wide range of expertise in powder metallurgy, material science, solid mechanics, thermal fluids, robotics, and machine learning. To gain a complete understanding of the final product, we use experiments and models in conjunction to understand the physics. Let me see. I don't think you guys have seen that. Okay, here we go. To understand the physics at different scales every step of the way in the process. So this procedure kind of helps us evaluate and refine the process to develop new equipment, optimize spray procedures, develop new materials, and qualify cold spray procedures as well. We work closely with our partners in academia and government and industry to strengthen this approach. Today, we will be going through a subset of this approach to understand factors affecting particle flight and impact conditions. So once validated, computational fluid dynamics simulations can be a great tool for predicting exactly what's going on at the impact site. And this is important for improving cold spray procedures overall and optimizing procedures as well. So today we'll be looking at 3 different cold spray procedural cases and evaluate how our models are doing currently and how we can improve these models so that we can get better information out of them. Okay, so the experimental methods that we'll use to validate or we used for validating cold spray models were a high watch velocimeter, and we also set up a Schiller imaging system in our laboratory to visualize shock diamonds that occur in the spray jets downstream of the nozzle exit. And in experiments, we took velocity measurements at roughly 25 millimeters downstream of the nozzle exit. And so we'll be using particle velocimeter to validate particle tracking calculations and the Schiller images to see how our models are doing for calculating gas dynamic conditions. So the 3 different spray conditions that we'll look at in this presentation are for spraying aluminum 6061, using helium and nitrogen using the VRC Gen 3 cold spray system, and also a copper powder, a tri-state copper powder using the Speed3D light speed system. As Aaron Bird had mentioned earlier in his presentation, particle size distribution is very important for determining what the spray procedures should be, but they're also important for making a one-to-one comparison between CFD simulations and what the high watch velocimeter measures. And we did a thorough particle size analysis, particle size distribution analysis, in what the actual size distributions look like and what the high watch velocimeter measures. And what we see is that the what HiWatch system measures is closer to the volumetric distribution of the powder. But the distribution kind of changes depending on the turbulence conditions at the exit of the nozzle, depending on what kind of spray parameters we have. So in our CFD simulations, we put in the HiWatch particle size measured particle size distributions, so that we can again have a one-to-one comparison with our CFD simulations. The 3D CFD models that we put in are geometrically accurate, as specified by the two manufacturers, and we're using Navier-Stokes equations to calculate the fluid mechanics, and with a realizable K-omega SST turbulence model. The estimations that we're getting for particle velocity are representative of the geometrical location where the HiWatch system measures particle velocity flight conditions, so that again we can have a one-to-one comparison. Okay, so here are some initial HiWatch versus computational fluid dynamics simulation comparisons. What we see here in the three plots are the measurements and CFD simulation outputs that we see from the three different spray conditions. The size-dependent, we're plotting size-dependent particle velocities. The red dots represent the HiWatch measurements, and the black circles represent the CFD simulation outputs. What we see here is that the size-dependent velocity estimation from the models are way underestimated, and in all three conditions. So the original thought that we had was potentially the particle sizes are the smaller particle sizes are being represented as large particles by the HiWatch system. Because when we put in the actual particle size distribution of the powder into the CFD simulations, we got, luckily, I think, an exact comparison between the CFD average velocity and the HiWatch average velocity. But after talking to the system manufacturer, we ruled this out. It's highly unlikely that such a big discrepancy is occurring in the size measurements. So the next thing we looked at were gas dynamics, whether we're capturing that correctly, and the other one is looking at particle dynamics and see if whether our simulations were capturing that properly as well. And so evaluating what's going on within the CFD simulations, what we did was compare the shock diamonds that occur at the nozzle exit in actual experiments and compare them with the CFD simulations. The CFD results were very good in comparison with the Schlerin images that we took in the experiments. There were slight differences, and this is expected, but the mismatch is not sufficiently high to explain such a big discrepancy in particle size estimations. So we go back and take a second look at how we're measuring the particle size distribution, and also how the particle morphologies look like. What we see when we take a closer look is that the powder particles are actually much more off-spherical than we think they are, and this can make a huge difference in the calculation of the drag coefficient and effectively lead to miscalculation of the particle flight conditions. So we wanted to measure the particle size distribution in our two powder batches, but this is not such a straightforward calculation, so we have to make some estimations. And we have transmission microscopy available to us in our lab, and the simplest measurement method is division of the nominal diameter of particles with its major axis. And that can give us a rough estimation, but in reality, you can make a much more complex measurement of these powder particles by taking a third dimension. So you would take the minor axis, the major axis, and the median axis, which is a third dimensional measurement, and do an estimation that way. But this is sufficient for a first iteration analysis. And we see when we look at the particle size distributions is that the sphericity changes between 0.5 and 1, and there's a large distribution there, and 1 is equal to spherical, so there's a lot of non-spherical particles in our powder batches. When we put those size or shape distributions back into our CFD simulations, now, interestingly, we are overestimating velocity in both aluminum cases, but we're actually doing really well with the copper case. The size-dependent velocity distributions are appearing to be much more accurate as far as the standard deviation goes, but we're still overestimating the drag coefficient here. So what this tells us is that we probably need to do a much better job measuring our particle shape distributions. So we'll go through this approach once or twice more and refine our measurement procedures so that we can fine-tune these CFD simulations. Some of the major findings from this work is that particle shape, generally not measured in cold spray, is an important factor for the flight conditions of particles within the nozzle and at impact. Particle shape measurements should certainly need to be refined to increase the accuracy of the models. What I'm not showing here due to the time limitation is that the bow shock actually affects the off-spherical particles a lot more when they go through when they go through that stagnant region ahead of the substrate. The same type of refinement procedure was done for impact mechanics simulations to figure out the bonding energy and figure out the deformation mechanics of particles upon impact. And since these models are calculated with the information we're getting from CFD simulations, what we can do is do a much more refined analysis of what these different shaped particles are doing to our cold spray products, so we can actually improve our process, perhaps improve the powders, or adjust our parameters accordingly to compensate so that we can tailor the cold spray products accordingly as well. With that, I will thank our sponsors, U.S. Army Research Laboratory and Herrick Foundation based out of Michigan, and I'll take questions. Thank you all for your attention.
Thank you, Ozan. So one question came in regards to where do you see this being applied?
Where do I see this being applied? Yeah, a lot of times we assume spherical particles when we determine the process parameters, and we assume a certain particle impact velocity, right? So this is a parameter that we need to take into account. So depending on the manufacturing process, perhaps the shapes are changing, so that then we would need to refine our parameters to compensate for that shape distribution as well as particle size distribution. So the size distribution is one thing, and that's what we're paying attention to for the most part. But shape distribution also has a huge impact on particle impact velocity. So,
yep, and you're absolutely correct. And yeah, that's a very good point to make, because it all comes down to what? It becomes down to, particle deformation. And those deformation characteristics are going to be influenced by a number of different variables, including, particle size, geometry, conditions, etc. So appreciate it. Thank you very much, Ozan. And I'd like to go to our next speaker. It's from Honeywell. It's Eric Shabilowitz. And he's going to be talking about chrome replacement repair,